Hello, this is your science teacher, Miss Green, in case you have forgotten who I am. We did have a Zoom class meeting today, and I understand stuff happened, so if you were not able to show up, that's okay. But of course, it's not showing up because of certain life circumstances, not because Call of Duty was more important or sleeping in was more important, okay? So I'm going to go over some of what we went over in the Zoom meeting slash a little bit more. So namely this week, we really were practicing balancing chemical equations as well as converting mass to mass, okay, and from moles to mass or mass to moles. And so this is going to be a little bit different than what we have been working with before, right? Because we are now introducing this sort of idea of balancing equations to then get something called a molar ratio to now connect these different bits of information. Okay, so this is probably one of my favorite parts of chemistry because it's a lot like just doing a puzzle, right, and problem solving. And so hopefully you'll enjoy it as much as me, maybe not. But regardless, I hope this video will be helpful for you. All right, so first thing, if you have not already checked out the video I posted of another teacher kind of going over how she does her balancing of chemical equations, I'm gonna do just a brief summation of it. What she does that I do myself, which I really like, is something called a T-chart. Literally just looks like a big old T, like, and that's the T, sis. I'm funny. Okay, so first what you want to do is have your T-chart, because this is basically like a bookkeeping system, right? So we want to try and conserve whatever mass is over here. So what that means is the number of atoms of all species on your reactant side needs to be the same number of your different types of atoms and species on your right-hand side, right? So the conservation of mass states that no mass can be created nor destroyed, right? So even when you burn things, right, it's not that matter is just all of a sudden, poofed, right, and not existing anymore. If we were to have a closed system and conduct a combustion reaction, right, basically just setting things on fire, you can collect the gas and the soot, right, and you're able to sort of have a before and after of this is the stuff before it was burnt, this is it after it was burnt, and they should have the same mass, right? All the stuff that's floating within that closed system will contribute to that mass, okay? And so this is obviously conducive to everyday life, right? The reactions that are happening in our body right now, what happens when you eat, what happens when you bake, what happens when, our water is interacting with different surfaces of the environment. So this is huge, okay? So we're gonna go ahead and do our bookkeeping. So I'm basically just gonna go through and count how many of each type of atom I got. So first we have our nitrogen, okay? So we have nitrogen on this side, we have nitrogen on this side. So on this side, I got 2. On this side, I got 1. So right away we can see this is not balanced. Okay, so we're gonna have to do some sort of manipulation of how many moles we have to be able to get this to have equal numbers of nitrogen on either side of our equation, okay? Next, we have our hydrogen. We got 2 guys on this side. We got 3 on this side. Another indication, things are a little jank, a little funky. Speaking of jank, I need to show you my camera setup at the end of this video. Maybe I'll post it to our Google Classroom because it is the funniest dang thing I've ever done. But you know what? It works. So usually you don't want to start manipulating your compounds or the guys that are made up of your multiple atoms, right? Or atom types, because that can get really hairy really quickly. So usually you want to work with your elemental guys first. But well, let's go through Ms. Green's thought process, okay? So I have 2 nitrogens versus 1 nitrogen, okay? So let's just say for funsies, we go ahead and say times 2 to get this to now be 2 nitrogens, okay? But here's the thing. here is the thing, is if I multiply 2 times my nitrogen, that nitrogen is connected to a hydrogen, or 3 to be exact, right? So whatever we do to our little nitrogen, we also have to do to this hydrogen, okay? So when I put this 2 out front, let's just say for fun, we'll say it's 2. It's going to be 2 nitrogens, okay? And now it's 2 times 3 hydrogens, okay? So this is also times 2. And this 3 then turns into 6, okay? So we're still not quite balanced, right? So our nitrogens are good. They're looking cute, okay? Hydrogens, you got 2 versus 6. Not so cute. Not a look, okay? So I have to start to think, what can I do, okay, to this hydrogen? Because luckily for us, we have elemental hydrogen. It's by itself, so we can manipulate it individually, right, separate from the nitrogen, okay? So what I'll do is I'll simply multiply it by a factor that will now match the number of hydrogens on the other side. So what we'll do is oh no, I picked the wrong color. No, it must be color coded. Must be beautiful. 2. Yes, blue. So now times 3, and that takes us from 2 hydrogens on this side to 6. Aha! So now these guys match and these guys match. It's a beautiful thing. But now we need to make sure that we're representing the changes, okay, that we made. We are going to keep the 2 here because that seems to check out, quite literally, get it checked out. And then on this side, we need to represent the manipulations that we did, of which the 2, right, that's from the beginning. So we did not do any sort of manipulation whatsoever. So you can say that there's an implied 1 in front of the nitrogen, right? So normally you would not put the 1 out front, right? If it's blank, it's implied that it's 1 mole of whatever you're talking about. But for the sake of perhaps maybe a multiple choice assessment, if I ask you what are the coefficients of this equation to get it balanced, you're going to say 1. Okay, that's going to be your first coefficient. Then when we get to our hydrogen, okay, our little guy, we had to manipulate it using a times 3. So what that means is I have 3 moles of my diatomic hydrogen here. So 3 times 2 is that 6. That's how we got this to balance, okay? So I would like y'all to do the practice problems that I had given you, of which I will help you do one of the problems that is like a word problem, so you don't have the equation quite yet. So we'll see how well that goes. So yeah, so let me go ahead and do some examples from the Mass to Mass stoichiometry problems. Homework.